Now imagine that we have our inductor that is connected to some charging circuit, and then it's connected to a Norton equivalent circuit where there's some resistance there and there is a current source. If the switch is closed and the circuit is at steady state, meaning we're at equilibrium, the switch being closed gives us just a wire here. At steady state, the inductor is going to act like a wire there as well. So in this case, we'll have a current flowing from our current source from the Norton equivalent circuit, and then we'll have some current flowing from the powering circuit as well. If we combine two of those together, we're back to where we were before. We'll have some starting current I0 flowing in that inductor from one source or the other. And how it gets that current doesn't really matter. Once we open the switch, the current is what it is, and that inductor will drive the behavior of the rest of the current. Once we open the switch, the current will be through the inductor. We know that the current through the inductor at T0 plus, just after the switch has been thrown, that current is still going to be I0, but then the current is going to start dropping off, and it will be a function of time. The inductor is going to push current through as long as it can, but long term it will dissipate all of its energy, and at the new equilibrium, the current through the inductor will just be the current from the Norton source. So we have our circuit. We established a current I0 inside the inductor, and once we open the switch, then the charging circuit is out of the picture, and the only circuit we need to worry about is this right here. We have a current from our Norton source. We have a current through the inductor, which we'll call IL because it's going to be a function of time. And let's go ahead and give ourselves a current through the resistor as well. And then if we have currents through the resistor, we're going to have a voltage across the resistor, and if we have the current flowing into the inductor, we give the inductor its voltage as if it's a passive element. And remember that the current obeys Ohm's law, and the inductor has its own characteristic equation. And so what we want to do here is to try to relate the inductor to the rest of its circuit. We need to remember that the inductor current is going to be a function of time, and the inductor current is the characteristic parameter that's going to control the behavior of the whole circuit. So we want to do circuit analysis to tie all of these together, and we want to do substitutions as necessary to bring everything back in terms of the inductor current. So looking here, I have my Norton current flowing up. Some is going to go this way, some is going to go that way, and so I can apply KCL and say that that Norton current is going to be equal to the sum of the currents through the resistor and the inductor. So I have the current through the inductor already. I want to have an equation here in terms of that variable. The current through the resistor is not in terms of IL, so we're going to try to write it in different ways. I can say that the current through the resistor is in terms of the voltage across the resistor. And I can say that the current through the resistor is the voltage across the resistor divided by R from Ohm's law. The reason I do that is that I notice that the resistor is in parallel with the inductor, so the voltage across the resistor is the same as the voltage across the inductor. And I can take the voltage across the inductor, and I can write that in terms of the inductor current. And so here I've derived a differential equation. The Norton current is a constant. L and R are constant values, and I have a differential equation for my inductor current. So what I'm going to do here is solve for di over dt, and then I'll be able to use a separation of variables to integrate. Now to separate variables, I'm going to multiply both sides by dt. dt and dt cancel there. I have a di on this side and a dt on this side. If I'm going to integrate this side di with respect to the variable I need to move my I over to this side. And so now I can integrate both sides. I can integrate my I, which is a function of t, with respect to I. These are constant, so I can integrate those dt. What I'm going to do is replace all of my variables with my scripted variables, my scripted I and my scripted t, because I'm going to integrate from my starting point the current that I have at the start, which is I0, up to the current that I have at some later point in time, and I'm going to integrate the time that I have at the start to my time at some point later. So this was my initial condition. I had to know the current at the beginning when the switch is thrown, and that tells me what the current is as a function of time because this is some arbitrary variable. If I'm integrating 1 over I, that's going to give me a natural log function. In, recall, is a constant. And I'll get the same thing for t. Now I will plug in values. And note that I'm missing a negative sign there, and there from, should have been a negative sign there to begin with. Now when I take both sides to the power of e, those cancel, and I have e to the power of negative r over L t minus t naught. Now I have this term here. I'm going to multiply over the bottom, so this goes away, and it's multiplying the e naught there. And then I'm going to add in to both sides to get il by itself. And so if I put all of that together, I get this. And so I come up with the current through the inductor as a function of time. Notice a couple things here. When t equals t naught, then we have this term is e to the 0, that's 1. And when t equals t naught, that tells us that our current is going to be in plus I0 minus in times e to the 0, which is 1. And so in plus I0 minus in is going to equal I0. And so our starting at our starting time, our current is the starting value. If we let t go to infinity, that means that this term will go away completely. We'll have an exponential decay there, and at t goes to infinity, we'll only have that term left, and our current will be in, because it will be just, the inductor will be just directly connected to a Norton source. We can simplify this equation a little bit here. This again assumes that t naught equals 0. That's typically going to be the case. And again, tau is the time constant, that is L over R. Recall that R is the equivalent resistance if you have more than one resistor. But essentially what we're going to do is find the Norton equivalent here connected to the inductor. And so part of finding that Norton equivalent circuit will always be finding the equivalent resistance there. This is an exponential decay, but it goes the opposite way. We are subtracting away from a constant value, and so we have an inverted exponential decay. So if you look at the initial change of the current, you'll see that it's going up very quickly, and it's going to cross that equilibrium value at one time constant, but you have to kind of eyeball that. That's difficult to do. What's a lot easier to do is recall that the voltage across the inductor is the derivative of the current. And so if you start with this function here and you differentiate it, this is a constant that goes to 0. This will stay put because it's a function of t, and so the voltage is going to end up being an exponential decay term. It's going to go like an exponential decay term. And so you can do the same thing as we did before. If you draw a straight line following the initial change of the voltage, it tells you approximately where the time constant is so that you can estimate that. So to recap, if you want to find the step response of an RL circuit, you need to determine the initial inductor current. This is going to be coming from whatever circuit the inductor is connected to at the very beginning. Then you throw the switch. You want to look at the new circuit with the switch in its new position. You'll find the Norton equivalent circuit connected to the inductor in that new circuit, and then the time constant will be L over R, where that'll be your Norton equivalent resistance. The final value of the inductor current is going to be the Norton source current that you have, because the inductor is just directly connected to that source current. And then once you know these three values, each one of them is going to go into this equation that we've derived. And so you can plug in all of those numbers and you have the inductor current as a function of time. Once you know the inductor current, you can find any other quantities, any other voltages or currents elsewhere in the circuit based on this initial setup.